Chapter 9. The Normal Probability Distribution. In the previous chapter, we stated that a random variable is of the continuous type when its values are numbers in an interval or in some cases union of intervals. For example, the weight of your school bag can be any number inside a certain interval, for example between 2 pounds and 18.5 pounds. Thus, the weight of the bag can be modeled as having a continuous distribution. Similarly, the speed of a passing car and the amount of sugar in your coffee can be modeled by using continuous random variables. In the discrete case, we can represent the probability distributions by histograms. In the continuous case, we use continuous curves to represent the distributions. These continuous curves are graphs of functions called probability density functions. We use probability density functions to help us determine the probabilities in the continuous case. The function f of x is a probability density function of a continuous random variable if and only if the following three conditions hold. 1. For any real number x, f of x must be greater than or equal to 0. This means that the graph of the function f of x is always above or on the x-axis. 2. The total area above the x-axis and under the graph of f of x is equal to 1. 3. The probability that a random variable have a value between two real numbers, a and b, is equal to the area under the curve and above the interval ab. This is illustrated by the red region in the figure. In this example, a continuous uniform distribution over the interval 2, 8 is introduced. The probability density function is constant on this interval and must be equal to 1 over 6 to guarantee that the area under the curve is equal to 1. This is the area of a rectangle with a base 6 and a height 1/6. So its area is 6 times 1 over 6, or 1. In part A, the random variable takes a value greater than or equal to 4. The probability of that is the area of the blue rectangle, which is 4 times 1 over 6, or 2/3. In part B, we see that only a line segment corresponds to 4 under the graph of f of x. This means that the area under the curve is 0, and therefore the probability is 0. In part C, the probability is given by the area of the green rectangle, which is 3 times 1 over 6, or half. The normal distribution is the most important distribution in statistics. It was discovered when mathematicians were studying errors in measurements. The probability density function f of x is given here together with a typical graph of this function, which we usually refer to as the normal curve. The graph of the probability density function f of x of the normal distribution is a bell-shaped curve which is symmetric about mu, and it extends indefinitely in both directions. The parameter mu also represents the mean of the distribution. The parameter sigma represents the standard deviation of the normal distribution. The tails of the normal distribution drop quickly in such a way that almost the entire area under the curve lies within 4 standard deviations of the mean mu. If mu equals 0 and sigma equals 1, then the normal distribution is referred to as the standard normal distribution. The mean mu is a measure for center, and the standard deviation is a measure of the spread or variability. The values of mu and sigma completely determine a normal distribution. In the figure, we see 3 normal distributions with the same center at mu equals 0, but with different standard deviations. Notice that the larger the standard deviation, the more the spread. Any value of a normally distributed random variable can be changed from the original x-scale to a standard unit or z-score by subtracting the mu and dividing the result by sigma. In fact, we are transforming a given normal distribution to a standard normal distribution. Probabilities involving a normal distribution now can easily be found by using the z-scores and Table 1, page 495 in your textbook. This table gives the area under the standard normal curve between 0 and a z-score. The probability density function of the standard normal distribution is symmetric about 0, and the total area under the curve is 1. It follows that area under the curve and to the right of 0 is equal to 1/2, and the area under the curve and to the left of 0 is equal to 1/2. We can answer the question here by using Table 1 to find the associated probabilities. For the first area, we use Table 1 to obtain 0.4332 for the yellow region in the graph to the left. But the area to the right of 0 is 0.5. So the red region in this graph has an area equal to 0.5 minus 0.4332, or 0.0668. In a similar way, and by using Table 1, we see that the red area on the graph to the right is 0.5 minus 0.4772, or 0.0228, which is smaller than the first area. Table 1 does not contain negative values for z, but we can use symmetry to help us find probabilities associated with negative values of z. In this example, we see that the area under the normal curve from negative 1.66 to 0 is the same as the area under the normal curve from 0 to positive 1.66. This later area can be found in Table 1 to be 0.4515. To find the area to the left of z equals 1.3, we split this into two parts, the blue part to the left of 0 and the green part between 0 and 1.3. The area of the blue region is 0.5, and from Table 1, the area of the green region is 0.4032. Therefore, the answer is 0.5 plus 0.432, which is equal to 0.9032. Using Table 1, we found that the area under the standard normal curve from 0 to 0.77 is 0.2794. But from symmetry, the area under the curve from negative 0.77 to 0.77 is twice the area under the curve from 0 to 0.077. Therefore, the answer is 2 times 0.2794, or 0.5588. In this example, we see that the area between negative 1.39 and 0 is the same as the area between 0 and 1.39, which is equal to 0.4177. So the answer is 0.5 plus 4177, or 0.9177. The symbol z sub alpha represents the z value so that the area under the standard normal curve and to its right is equal to alpha, where alpha is a number between 0 and 1. Again, Table 1 can help us to find such values, as you see here in Example 7. To find the probabilities associated with a normal distribution in this example, we first convert the given values of x to z-scores, and then use Table 1 to obtain the probabilities. In Part A, we convert 89.2 to a z-score by subtracting the mean 82 from it and dividing the result by the standard deviation 4.8. We get 1.5. This means that the probability of x less than or equal to 89.2 is the same as the probability of z less than or equal to 1.5, which is 0.9332. Similarly, in Part B, we convert 78.4 to a z-score of negative 0.75 and use Table 1 to find the answer, which is 0.7734. In Part C, we need to convert both 83.2 and 88 to z-scores. The corresponding z-scores are 0.25 and 1.25. Then we use Table 1 to get the shaded area in the figure to the right, which is equal to 0.2957. The normal distribution can be used to approximate the binomial distribution. If x has a binomial distribution, then z, which is obtained by subtracting the mean NP from x and dividing the result by the standard deviation, has a distribution that is approximately standard normal distribution, provided that n is large enough. This fact can be used to approximate probabilities associated with a binomial distribution by using the normal distribution. This should be done if both NP is greater than 5 and n, 1 minus p, is greater than 5. A continuity correction is required when we approximate the binomial distribution, which is a discrete distribution, by the normal distribution, which is a continuous distribution. Notice the probability of binomial random variable. Assume the value k is the same as the area of the histogram bar above k. This is approximately equal to the area under the normal curve from k minus 0.5 to k plus 0.5.